So today's lecture, I'm going to talk about called population coding. It's basically how information is carried by a group of neurons, a population of neurons. As you know, for individual neurons, they tend to be very noisy, and you just look at activity of a single neuron, your information about some variable that's coded is not very accurate. Right? This is a very good example. It's called a tuning curve in the motor cortex. In this case, the animal is doing a reaching task. The animal's hand is a monkey. It's in the middle. So on the table, there are 8 different directions the hand can move to. Or the center out is a reaching task. And these are the raster, the spikes, in repeated trials of the animal moving in different directions. So based on this, you can see the activity of the neuron. This is the average firing rate as a function of movement direction. You have this very broad tuning, called tuning curve. So the tuning curve means the average firing rate as a function of the encoded variable. Right? The error bar would be like a noise. Right? That's because if you repeat the trial, every trial the number of spikes is actually different, right? Because of the noise. Of course, there are different neurons. They like they have a different preferred direction. So that means, based on the activity of this single neuron alone, you're not that certain which direction the animal is actually reaching. Right? You know this roughly, maybe in that quarter, but not the exact direction. It's not very accurate. But the animal's movement, because the motor cortex activity presumably controls the movement of the hand, right? The actual movement can be very precise. Right? This is very typical. So not say this is the worst neuron. A typical neuron in motor cortex, their activity, how they depend on the direction of movement, looks like this. It could look like a cosine, we call cosine tuning curve. Right? It's look like a cosine function. It's very broad. So these are very typical. So the question is, if your actual hand movement can be much more precise than this, right, then that means you have to pull information from many neurons. Right? This is one example because of population coding by a population of neurons. So that just shows that this cosine tuning curve actually quite common in the motor system. But this is the motor cortex. There are many neurons. The average, you got something like this: the basal ganglia, the cerebellum, and it's all related to the motor system. Somotor sensory cortex is like a sensory cortex. Also, this kind of tuning. There's just little notes that a cosine tuning function look like this. The function, the cosine function, there's a coefficient. There's this called the background firing rate, or the average firing rate. There's a better fitting. It's called the von Mises function. Some people call it circular normal. It's basically a cosine function, but raised to the power of e. So in that case, it actually looks like a Gaussian. It ranges from a cosine to a Gaussian function. It's almost like Gaussian because if you make a decomposition, like say Taylor's expansion of theta, for the cosine, the leading term is a quadratic term, right? That's a Gaussian. So this is just like that's one note. So typically, tuning is very broad. That's for sure, right? So I just give you a few more examples in different sensory modality. You see that this is the general problem. That if you want to code information, you need many neurons, just because the precision of a single neuron is not that precise. So this is the receptive field, somotor sensory cortex of a monkey. This is a macaque monkey, right? So each of the oval is a receptive field of a neuron in the somotor sensory cortex. So that's sensitive to touch, right? or tactile stimulation. Of course, these receptive fields, they are overlapping, right? So the tips, maybe the receptive field is actually smaller maybe than this thing in here, maybe slightly. But you see that if you can distinguish something, like say there's one needle versus 2 needles on your fingertip, right? So it's much more precise than the size of the receptive fields, actually, right? So you need to, if you distinguish something very, very fine, very small, difference very small, you need to use the information from multiple cells. This is some of the sensory example. This is a visual example. This is visual cells from I think it's from squirrels. So this is you're staring, say here, On one side of the cortex, they code information on the opposite side, and you already know about that, right? So each of the oval here is a receptive field of a neuron in the visual cortex, right? So here there are many of the cells put together. You can see that over the fovea, that's where you're looking at, that the receptive field size is much smaller, right? You go to the periphery, the receptive field size is much bigger. So people, you can distinguish things really fine. For example, if I give you two lines, two broken lines, they're either aligned with each other or slightly offset, almost parallel, right? You were very good at this task. So there's even the two lines that they're slightly misaligned, you can tell. It turned out that the acuity, how much difference you can tell, that's actually small. When project on the retina, actually that difference is actually smaller than the size of the cells on your retina, smaller than the sensors. Right? That means you really need to pull lots of information to do the fine discrimination like that, all right? All right. So here's one method that I think is historically interesting. I think it's also very simple. It's called population vector. It started from actually at Johns Hopkins University. So today it's used in all different kind of situations. So this is the first use for that motor system, the motor cortical cosine tuning. So the idea in the beginning was that maybe, so each cells contribute to some direction, right, from motor cortex. And you have many neurons contribute, has a vector pointing toward the preferred direction. So if one neuron fire more, that means you try to push the hand in that direction more, and you should have a weighted average of all the cells. That the final big vector will determine which direction your hand will move. I think that's actually not the correct way to think of how the motor cortex works. But the mathematical method actually works, right, for this system and for other systems. The idea is that so first of all, you have a description how the neuron's activity depends on that parameter of interest. Here is the reaching direction. All right. So the activity, if you write, is okay, the activity above the baseline. Right? When you say this cosine, but plus another term, because otherwise the cosine function is positive and negative. The firing rate cannot be negative, right? You have a plus and positive number. So this is this activity above that baseline. All right. You just subtract the constant. So the activity is a cosine function, right, of some of your actual reaching direction theta compared with some preferred direction, so theta I for this neuron I, all right? So this, you can write this as a dot product, right, of a preferred direction vector and an actual direction, the reaching direction vector D. Right? You can write in this way. Okay, this is the way you describe how activity depends on the reaching direction theta, where you write the vector from like this. So the population vector is just like that. So each neuron, you have a preferred direction. That's where the neuron like that direction. And you weighted by the activity above the baseline, all right? So this is just like a voting, right? So each cell is a vote to their preferred direction. And the vote is proportional to the activity. If your activity is higher, you proportion more. If the activity above baseline is negative, right, the cosine function can be negative, it goes in the opposite direction. So this is the first use as a way to actually read out information. If you record your activity from a bunch of neurons, I want to read out what's the true reaching direction. This actually works. This is an example. I show there are several hundred neurons, I guess. So in this diagram, I just explain. So each of the black line is a preferred direction of one neuron, all right? So this for 8 different reaching directions. So for example, this neuron, you plot the curve, so this preferred direction like this. So in this diagram, it's still the same neuron, same preferred direction. Here, I guess, so this one. But it's weighted by the activity, just what we said before, right? So this one, if you reach the direction, this neuron has a very long, direction. If you reach the opposite direction, the neuron actually becomes negative, right? Then you just do a vector, just as a vector sum. You just average the weighted sum. And the result is this red vector. That's called the population vector. It's based on the activity of all the neurons. So you see it compared with the actual reaching direction, kind of similar, but it's not exact. You see there's some errors there, right? Of course, you will ask question, maybe this method is not the most accurate, but it's actually turned out to be true, right? But you say, how accurate can you possibly read out the information? You know, there are many different questions. But this is, I think, historically, I think the first method that's used to read out information from a bunch of neurons. But in this case, you say, oh, why do I do this? This doesn't, you know, because I already know what's the animal's reaching direction. Why you do this? But you can do something more interesting in some other situation. So this will just first show you this method works in 3 dimensions as well. Right? If your animal, say the hand is in the middle, you reach from a center reference point to a different direction in 3D space, you have that preferred direction vector as well. All right. So actual frame rate, they also have a cosine tuning because it's still that dot product, right? From the preferred direction vector and the actual reaching direction. So if they're aligned, you have a maximum response. If you move away from that preferred direction, it drops off according to the cosine of the angle, right? It's the same idea, it's in 3 dimensions. So the mathematical formula is exactly the same because the dot product vector works in any dimension, right? And you can do this too. I think this is maybe the red population vector. That's the true reaching direction vector. It works in 3 dimensions as well, right? These are the real data. So here shows why this method works. This is a very simple argument. So if so here's the statement. So permanent vector always recover the true reaching direction exactly if this condition is satisfied. All right. So this condition, you see here on the left-hand side, that's a preferred direction vector. We just like in MATLAB, we assume it's a column vector by default, right? This transpose, it's a row vector. So this product, this is actually called the outer product of vectors, right? So not the inner product, dot product. This is the outer product. When you do this, you got a matrix, right? This is like a correlation matrix. So if these matrix, if add over all the cells, I is the identity matrix, then this thing works perfectly. Okay. So when these conditions, these things actually become identity matrix. For if suppose you have a bunch of this preferred direction vector, if they are distributed randomly in all directions in a uniform manner, right? So on average, you get something like this, very likely. But in reality, it's roughly true, but not exactly. There's some skewed direction. But this is almost satisfied in real situation for the motor cortical direction. So this sort of mostly correct, right? So why this thing works? So the mathematics is extremely simple because the population vector by definition is this weighted sum here. But here you write it this way because for this trick you want to play. So this is the scalar activity times this vector of the preferred direction, right? You write this way. This is the inner product, right? Of this is a row vector of preferred dot product with this d. So write this way, but you can get d outside of the summation. So you can see that if and only if whatever the sum inside the parenthesis is identity matrix, they become equal. It doesn't have to be equal. It can be proportional. And that's also okay, right? All right. So this is it's very simple. Is there any question so far about this? I think this is very straightforward. Simple linear algebra. So this method has been used in a mental rotation task. So because if you just do this reaching, you already know the direction. As I said, there's really no need to do it, right? For mental rotation, I think the original mental rotation task is like this. Suppose you have these blocks, so like a Lego kind of blocks, and there's some 2 different objects. The question is, are these 2 identical or not? Okay, so the people, this is when you do this kind of type experiment for people, this is a reaction time. So how long does it take you to say, okay, they are the same or different? This is the angle of difference. I mean, how much I need to rotate one object to look like the same as the other one. When they are very close by, you can see very easily, right? If you suppose the angle is 0, you are very fast. You can see the same or not. But if as the angle increases, look like there's the time increase linearly. So that people really, the idea is that you actually rotate one object in your mind, try to see whether it matches another or not. It takes some time to do that rotation. So here's a very simple one. You cannot ask a monkey to do that task exactly, but this is a motor version, like a reaching version of that task, but it's much oversimplified. But so it goes like this: the animal's hand is resting in some center location, all right, and then there is a visual stimulus. It turns on somewhere along the periphery of a circle, right? Whenever this thing turns on, well, in a simple task, you're just reaching toward that visual target. Right? That's a simple task. But this one is sort of a little bit of twist with the rotation. So the monkey will distract. If the light shines on, you don't go directly over there. Instead, you go toward an orthogonal direction, like a 90-degree, and turn towards the left. Right? Whenever a light shines on, you move to a different direction. So when you do this task, when you do this in a monkey, I think this is the motor cortex. So these are the population vector you got from activity of the neurons. Okay, and then you can compute that because first you have to measure the preferred direction each of the cells. Once that's done for this particular task, you measure activity, right, of these cells. So in the beginning, you see there's a little vector. In the beginning, activity is not that large, so the vector's length is kind of short. Eventually, it becomes longer and longer. Well, it seems like it's rotating, right? So all this time, this from 90, this time, this is I think milliseconds. All this thing happens before the animal actually make any movement. So the hand, you can measure EEG, the EMG to make sure the muscle is not working yet. You should the task, monkey it's prepare in the mind to move in that direction. Before the hand actually moves, this is what happens. You can actually see this thing actually happening, even though there's no behavior explicitly. The animal just sits there, right? So within a fraction of a second, you see there's a sort of like a rotation. So the prepare, so the vector pointing toward the reaching direction. Then there's and will start to move. Right? This is one example. You use this, you can see activities. Otherwise, there's no actual behavior. All right. All right. This is the video of hand position contraction by population vector. So this is the first you see this is the oscilloscope. I think from a single neuron in the motor cortex. Oops, it's not this one. Let me see. The animal is doing a circular movement of the hand. It's a monkey. It's very random. There's one big spike from the one cell. There are other cells very smaller from maybe farther away. So that shows you the actual spike is very noisy, right? That's just very typical. In this case, the monkey actually moves in a circular manner. So here, what you do is that when you make a continuous movement, so that population vector, you get a vector by move from one position to the next. So that turns out to be an increment. Right? You start from any position, you can compute where the hand is going to move based on population vector. Right? That's very similar to actual movement. When your hand move a little bit to the new position, you do the same trick again, right? Based on the activity at that moment, you can compute where the hand is going to move next. Right? If you do that, you can not just one direction, you can connect all the increments of the distance based on the population vector, connect them head to tail, right? Add them together, then you can compute the whole trajectory of hand movement. So this shows us when the animal doing, I think is moving in a circle. So that ball is a location computed by the population vector. Right? The actual hand move. This actually animal actually moving in virtual reality. You can ask the question if the visual field is distorted. Right? So your actual hand movement is it's an ellipse, but it looks like a circle. You know, how does the motor cortex follow the visual percept or actual physical movement? It depends on the cortex. There are different answers. You can do stuff like that. All right. So this example is all really pure dimension vector. But this is by the same lab, Andy Schwartz. They use point vector to control a robotic arm. So in this case, there's actually two images. On the left-hand side, it's a robotic arm. The left-hand side is the monkey's hand actually moving, trying to push different buttons, right? So this is the early example. It doesn't work very well, you can tell, but it's just, somehow the robotic arm actually is moving. If you use the population vector, you compute it based on activity you measure from the motor cortex with multiple neurons measured simultaneously. You use that to contract the population vector and use that direction to drive the robotic arm. Right? The idea is that if you can recover the true hand position, the arm should follow the monkey's movement. This is the early example. It's not, well, kind of moving, but I'm not sure it's exactly the same. So this is a more like a later example. This is actually better. The monkey is there. This arm is driven by the population vector from that activity from motor cortex. The monkey's real arm is not actually moving. The monkey learned not to moving, just thinking about moving, right? So it can do something useful actually. It can grab some food, but the grabbing is additional. When the population vector moves to the end, it automatically grabs. Otherwise, there's extra control. But the movement of the tip of the hand is controlled by the population vector. Yeah, it's sort of working. Well, it's kind of hard to move to the mouse or what, man? I think this is it's already useful, right? So even though it's by such a simple method. So you see, if you study the brain, if you find the activity of the brain somehow correlates with some physical variable, some variable you can measure, then you can do the reversely, right? Try to read it out, use that information to do something. So the science part really is the cosine tuning, right? You know there's the movement direction and activity have that relationship, and you take advantage of that. Try to read out the information to do something. To do something, that's engineering part of the problem. All right. So you may wonder why the population vector looks like that relies on the cosine tuning, relies on some distribution of the preferred direction. What's more general method? You want to say what's more accurate, right? This is a better method called optimal linear estimator. The final solution is sort of like an optimal linear mapping based on the pseudo inverse. So the idea is this: you use exactly the same model. Here you assume you have a cosine tuning like this, right? I wrote this like a preferred direction, a dot product with a direction vector, right? That's the same as before. We write in this vector matrix form. So this is the activity. How activity depends on reaching direction. Right? This is you assume this is true. So if you write this, each of the scalar equation, like this way, you can write as a matrix. So this P is a row vector, so this whole thing is a matrix. They call it the big P, all right? Write this way. So starting from this equation, you want to solve for the direction of movement D from the activity A, right? This is like a solving linear equations, right? Of course, this linear equation, as you see, I think this is the over-determined, right? You have this only movement on three-dimensional, but here you have many more neurons, right? You have more equations than the number of unknowns. Unknown is three-dimensional D, right? You have many equations, but they are, of course, contradict each other. There's also a lot of noise. So to solve the equation with standard method, of course, is a pseudo-inverse method, right? That's shown here by this. Right? So in this method, you no longer require that this thing has to be the identity like a matrix, right? You don't need to this kind of assumption. This is more general. It's usually better. So this method, of course, this will be the optimal method based on least square, right? Because this, as you know, this solution is related to the least square method. So given this equation, I want to minimize the difference between the left-hand side and the right-hand side, right? The norm, the square error between the two sides. You sum over all the entries. You minimize that, the result is like this, right? Let's minimize the square error. All right. This is just the same, pseudo inverse we use in different contexts. The best method is a benchmark that people use as maximum likelihood estimate, right? So I'm sure you encounter this. This is like this very typical method used in many different situations. So in this situation, it goes like this. You start with the probability. This is a probabilistic method. So basically, you have a model of how your response are, right? Depends on some variable x. The x could be movement direction or some stimulus, whatever variable is encoded. So basically, this probability distribution is basically I know how that response vector of many neurons, how they are distributed given that value of that stimulus or that encoded variable x. Right? Once I know that, you just try to find, so your data basically is a response based on the response of neural activity, the R, that's known. What I want to find out is what's that underlying stimulus where the physical variable was reaching direction that's encoded variable x. So the maximum likelihood just say they call this likelihood function, right? That's the probability that what they call. So in neuroscience, people would say this is how the response depends on the stimulus, right? How the response depends on your stimulus or on your variable. So maximum likelihood is just find the x such as to make your data most likely, right? That's what they say. It's the probability of your data. So that's called the maximum likelihood that you make your data most likely. So why is it called the best method? So the maximum likelihood actually it's if you have many repeated trials, many data, if the data set is very big. This method approaches they call Cramer-Rao bound in the limit of large. In the Cramer-Rao bound, I'll give you explanation in a few minutes. So that is the best possible square error you can possibly achieve for any unbiased estimator. So you cannot be better than that because there is inherent noise, right? Even though there's even though your stimulus is the same, you repeat multiple times, the response will be different from trial to trial because you have inherent noise. There is no way you'll figure out the exact stimulus perfectly. Right? There's always inherent noise. So the minimum amount of noise you can possibly achieve is just given by this bound. Right? So this mathematical method, at least in the large data, it reaches bound. It approaches that bound. Right? In some cases, it can be equal to that exactly. So that's in that sense, this is the best you can possibly get, right? So this is kind of an abstract. Let's give a concrete example. We start with the tuning curve. Right? This tuning curve is the average firing rate. So the R here is the number of spikes. Just think about it within a short time window. So the average number of spikes R is a function of the stimulus x. All right, this average is a tuning curve we showed before. All right. So this function, what is this function? It's the so-called likelihood function. So that means like this. So suppose the number of spike has a Poisson distribution, which is for discrete distribution, this is the most random you can possibly get, right? and real neurons distribution very close to Poisson. So you have learned that, right? Some Zhang lecture, I believe. So the exact form doesn't matter here, but they say this is a Poisson distribution. Poisson distribution has only one free parameter, it's the mean, right? So in this case, this is a Poisson distribution with the mean fx. So this mean, of course, this mean depends on the stimulus x, right? That's a tuning curve. So if you have a bigger mean, Poisson noise, the variance is actually equal to the mean. So you have basically you have a tuning curve. For the bigger response part, your error bar actually bigger. Right? That's what it is. All right, so this is just concrete example for this tuning curve. I'll give you another example. So Poisson noise. The Poisson noise is very easy, but let me just show you for the special case mathematical explanation. So I say population vector actually it can be, actually it's identical to maximum likelihood in some special cases. Here to give you one example, all right? So suppose I have a bunch of neurons, each has a tuning curve, this f as a function of the x, right? Has a reaching direction. It's a, I assume you have this dot product form. It's have a cosine tuning in this three-dimensional or two-dimensional space, all right? So I assume each neuron, all right, given a stimulus x, has some response, right? This response, you can see here, this is the Gaussian distribution. So the Gaussian distribution has a mean, right? There's a mean equal to this tuning curve, right? Given by tuning curve, because that by definition is a mean response, right? For different x. And the error by the noise, assume it's constant. This is sigma square. So that's the variance, all right? So you assume that the different neurons are independent of each other. So that means each neuron response is random, right? It has average, but in a particular trial, maybe response may be more than average or less than average, right? But you assume that different neurons, their fluctuation or their noises are not correlated. So if one neuron happens to fire more spikes than average, the other neuron can be either fire more or less. And now say if one neuron fire more, the other neuron also fire more, well, that would be like some correlation. So this is a simple assumption called independence, right? It means that given the stimulus x, the response of a bunch of neurons from 1 to n, their joint distribution is just a product of their individual distribution. And that's the definition of the independence in probability. What you got, because there's an exponential function in this Gaussian, then it's the same as you sum over all these square terms, right? So this is basically, we have this particular model for the neuron response. Assuming independence, we see how if we do maximum likelihood function, maximum likelihood estimation on this particular model, what result we get, all right? So for the independence, for real neuron, actually, let's say in cortex, the neuron actually correlated. Not a lot, by maybe a very small percent, maybe 2% or something, very small correlation. But that correlation has some effect on so how much it can possibly be accurate. But for our argument here, it really doesn't matter because there's very small correlation. So, all right, let's just assume the independence is true. So to maximize, so given this data, the response R, right? I want to figure out what's the stimulus X, right? So maximum likelihood, of course, I maximize this probability, make my data most likely. Where's the peak of this probability distribution? Of course, because it's a negative sign, the exponential function, it's equivalent to minimize the square error, right? To maximize, to find X and maximize this, to find X and minimize the square error. All right, so to optimize this, you take a derivative with respect to x, set to 0, you get a linear equation that looks like this. All right. Of course, this fx actually it's a dependent x in this way. So I'm not going to do this derivative, but this is just quadratic, right? It's a quadratic term. When you make a derivative, become a linear equation. And you see from here that when this matrix we saw it before, so our friend now, if this one equal to the identity matrix, your solution X is equal to this, it's exactly the population vector, right? So that means if your model like this cosine tuning is exactly true if your noise is Gaussian, which is not exactly right. Usually, if you give a neuron give a bigger response, you have a tuning curve, you get a peak, the bigger response, the noise also increases. It's more like a Poisson rather than sort of Gaussian. But if the Gaussian model as an approximation used that way, then to maximize the probability of the data is equivalent to minimize its error. But in this special case, when these things, the preferred direction distributed uniformly without second order correlation, then the solution is exactly the population vector. Right? All right, that also explains why it actually works, right? It is in this probabilistic way. So the first one we derived parametric vector more like based on argument from linear algebra. This one is more based on like a probability theory, right? It's okay so far? Any question? Clear? All right. Okay, so this is the optimal material. As you know that I'm not going to quiz you on this, but I'll give you an explanation. I said this one, usually people don't talk about this much, but I think here it's the perfect time to give it a very quick explanation. Right? So you said that method, okay, according to the Cramer-Rao bound, there is a lower bound. How can you prove that? How is that, you wonder, what would be the best method if I do this, why is that? What's the minimal error I can possibly achieve, right? So this gives you exactly that question. So this is based on the Fisher information. So there are two information that use most widely. One is the Shannon information, right? Another is called the Fisher information. So I'm not going to talk about Shannon information today, and just talk about the Fisher. So Fisher information is especially useful when you consider continuous variables. So Shannon information works for both discrete and continuous. This is only work for continuous variables, all right? So here we start with that likelihood function P with the response depend on stimulus. We start from that, okay? So people usually consider the log likelihood. This is called likelihood. They take a log, all right? So what you consider is that if I change my stimulus a little bit, how does that change my probability distribution? And you consider this derivative. They have a name. They call it a score function like this, right? It's just a scalar in this case. So we define the average, just average, because this is a probability distribution. You can average over the response. So I fix the stimulus the same. In repeated trial, response vary from a trial to a trial. I can do an average, right? Okay, so I just go through this so you get some idea. So this turns out this score function always averages to 0, because when you do this by definition, look like this. You make a derivative of the log function. It's a derivative divided by itself, right? And then you cancel each other. You got something look like that. You exchange the order of derivative and summation, because the probability always normalized to 1. It's a constant derivative equal to 0. So that's kind of a bit of clever trick, but it just shows this function is always equal to 0, average to 0, all right? So this is, first of all, you realize this is a random variable because it's a probability distribution, right? All right. So it means equal to 0. So its variance of this variable is called the Fisher information. All right. So why this is important? Well, it's important because of this Cramer-Rao bound. That's what this right here. So if you have any estimator, so your estimator, basically, think about this. Your population vector or your optimal linear estimator, what you got is basically you give me the response, you want to figure out, this is just a function that maps your response to a decoded variable, what's your estimated variable, right? It's just a function. It depends, the maps from R to this estimated variable. So an estimator is unbiased because even though your true X is the same, here just fix the true stimulus. In repeated trials, your response will vary from trial to trial, right? Of course, your decoder usually vary from trial to trial. If your decoder doesn't vary, this function is a constant. That's trivial, right? It's not interesting. Of course, it depends on response. It's random. So it's a random variable. Its average, of course, in ideal case, if you average, it should recover the true variable, right? And that's the best case. That's called unbiased estimator. If you're biased, that's it can be very wrong. The best one should be equal. So this is the theorem that says here is that Cramer-Rao bound says that for any unbiased estimator, I didn't say what kind of estimator this is, right? You give me any estimator, as long as you recover the true value on average, then the variance of your estimation, okay, because it varies from trial. Even the X is the same everywhere, but you just repeat the trial, your estimation, it depends on stimulus, depends on response, of course, it varies from trial to trial. Its variance should be no less, greater or equal than the inverse of Fisher information. Right. So it's basically the Fisher information defines, so this is basically a square error of your estimator, right, compared with the true value. It cannot be smaller than this thing. Right? That's the minimal thing you can possibly achieve. So it turns out maximum likelihood in general, in a large, maximum likelihood in general is not really, maybe you learn this in our probability class, it's not really unbiased. Sometimes there are biases. But if you, in a large number limit, in repeated independent trials, it approaching, on average, it actually approach unbiased estimator, and also this variance actually become equal to the bound. Right? That's possibly can achieve. Yeah, this is the proof. You say, where does this inequality come from? Inequality comes from this. It's square variable greater than this. This is the Cauchy-Schwarz inequality. You see this many times. I just say it is because any variable is square on average cannot be negative. That's based on that. So that's come from that. All right. And the proof, I'm not going to go through proof that if anyone wants interested, you can go. It's also very clever. It's also very simple. You can use that equality to prove that. Right? I'm not going to show this right now. All right. It doesn't, detail doesn't really matter, but it just shows you how this thing works. All right. All right. All right, I'll give you some examples of facial animation. That definition is very abstract. Again, for the concrete case we just considered before, what's that facial animation? All right, consider this case again. You have a tuning curve, just average firing rate, depends on your variable encoded. All right, you have a Gaussian distribution, and you have error bar everywhere, all right, for each location. So the score function, just by definition, you just take a derivative, do the stuff, you find out it looks like that. All right, so because you have a derivative, that's why this tuning function has a derivative here. Fisher animation, just by definition, you do that. What you got? This final result looks like this. All right, just show you the results. All right. Let's see the tuning curve. Prime means the derivative, a square. Okay. So first, make a derivative and square divided by the noise, the error of the noise, the variance of the noise. All right. So that you see, the Fisher animation is higher when the derivative is high. So in that case, if you, in intuitive explanations like this, suppose this is your variable is actually here, right? On average, your response is here. If the stimulus actually change a little bit, your response also change, right? You can, based on the change, you can figure out how much your variable actually changes. So this thing would be most sensitive if the slope is large. If the slope is large, a little bit different in the stimulus, you will see very easily in the response, right? So your error will be more, your estimation will be much more accurate. So the least amount of information happens when the derivative equal to 0, which should happen at the peak. So intuitively, you would think that the peak, because you have more response, it gives you most information about the coded variable. Actually, it's the opposite. That gives you least information, because if it's a flat, if it's totally flat, you change your variable, your stimulus change, the response is the same, right? It gives you no information at all. So it's kind of counterintuitive when you first think about this. So for the Poisson distribution, it's very similar. It's also the derivative square divided by the response itself. Response itself, you see, for Poisson distribution, the response is equal to the variance. So it's sort of actually similar to, actually the same as this. Right? All right, let's just give you some example for this Fisher information. All right, I think that's enough. So I give you example of population decoding from place cell population. So this is based on the same data we showed before, right? The bunch of neurons we already know. So based on this, based on activity, you can figure out what's the location of the animal, right? For example, this cell fire node is here, but some are more tricky. Like in the middle, there are a bunch of cells. How do you combine them? The method is the same. You can use population vector, right? You say, oh, where is the population? It's not three-dimensional. Okay. The bunch of pixels in the environment, each pixel in different location, you concatenate a big vector, that's a big vector. So based on activity, you can, weighted by the activity, sum them together, you can do the same trick, right? So the best method, of course, is the maximum likelihood, maximum likelihood estimation, right? So here showed, hang on, this is the, oops, okay. Yeah. So here, so the cross, the little cross is the position of a rat running in that maze. So the color shape is the probability distribution of the location of the animal, right? So based on the probability distribution, you say that given that activity, what's the most likely position of the animal? So it's like a maximum likelihood, right? So then you sometimes have error, but sometimes you can do it quite accurately, right? So this is you sort of expect this. So this is just the same thing that this is look at the activity. You want to see where's the location of the animal. You can see the animal moving around almost continuously, right? You can just, without looking at the animal, you know where animals actually moving. Of course, this is not very useful. Just like in the reaching, you already know the reaching. Why you want to do this? But you can do this, for example, during sleep. So if an animal is dreaming about running in this maze, you should be able to, if the neural activity pattern is the same, you should be able to recover the animal's position, right? So what's the animal doing exactly? So in this case, during the sleep, it's different. This is like you look like it's a motion, but actually it's just a visual illusion. It's just jumping around discontinuously in this example. Yeah, but if the animal really, the neural activity replay, if it is same, is very similar to where you have been. Sometimes you can dream about go to some familiar places. I bet in your brain probably the activity is similar. In that case, if you get the activity, you should be able to recover actual movement trajectory, right? So this, let's see what this one. Yeah, here's something more interesting. That's from, it's my last video. Show you from Pfeiffer and Foster at Hopkins. They moved away, but so in this case, they're in the hippocampus. The place cells. When animal is standing still, when animal not moving, there's activity in the brain. There was an activity I didn't tell you called sharp waves. So within a fraction of a second, animal can think about something else. People may suspect it's useful for memory consolidation or either like a planning for future paths. Because otherwise activity is always depends on your current position. You cannot think about the future position. In this case, they do the similar thing. This maximum likelihood, sometimes they call it Bayesian method. You can add some prior, make them more accurate, but same idea. So the icon, that's the actual location of a mouse, of a rat. The hot spot is activity, so the position of animal-based activity. So what do you want to see here? This is maybe 100 times slowed down. So the animal is standing still in a fraction of a second. They're thinking about moving somewhere else, right? This is the actual movement. The animal is actually moving. This is almost in real time, moving in different spaces. So the trajectory of this animal is standing still, the animal not moving, but they were thinking about somewhere else very quickly. So it might be like a past planning or something. So this actually showing the way. Behavior, this animal actually moving. So you sort of, sometimes you have error, but you roughly know where the animal is. All right, so you got the idea. So these are just shows you, how can information coded by a population of neurons, not a single neuron, a bunch of neurons, right? How can you read out that information if you know how the activity is correlated with some coded variable? So, but like a feature information, those stuff, that's optional material, but I tell you that's sort of how accurate can you possibly be. The population vector is very simple, but sometimes it's equivalent to the population to the best method, but typically it's less accurate, but it's very convenient to use. It's very simple. It's easy to implement even in neural hardware. Right? I think that's all for today. Thank you.